We're about to move into talking about multi-threaded software, and I always like starting with the operating system mechanics because they really give us a good understanding and background for how all this multi-threaded software is going to work, even in Go, which is sitting a layer above the operating system. And there's a bunch of terms that we're going to need to define along the way as well, like what does concurrency actually mean? What does parallelism actually mean? And concurrency, we could start with that right now, means out of order execution. That's really the only thing that I want you to keep in your head. The idea that we have a sequence of instructions that we're looking to execute from beginning to end, but we're going to execute them out of order, still get them all executed, and hopefully get to the same result. So we're always going to be thinking about out of order execution when it comes to concurrency. Parallelism, that means that we're executing two or more instructions at the same time. It's about doing a lot of work at once. And what's interesting is sometimes these terms blend into each other. Sometimes they're just polar opposites. And we'll figure out when that is as we continue to talk about OS and then Go scheduler mechanics. But let's focus on what we need to know about the operating system. So let's say I was asking you to write an operating system scheduler. What are the things that you need to kind of consider if you're going to be doing that sort of engineering? And one of the ideas here that we got to really cement ourselves in is this idea that we want to create an illusion that a lot of work is happening on the machine at once. In other words, we should be able to run multiple programs, multiple applications at the same time and create that illusion that they're all running at the same time. Now, physically, they're not going to be able to do that. It's all going to depend on the hardware that we have. And we can create some imaginary hardware for this as well as we learn our mental models. So let's start off with a very simple hardware where all we have is a single processor, and that processor has a single hardware thread. And let's represent that hardware thread as the ability to execute instructions. So every hardware thread that we have in the machine gives us the ability to execute instructions. So if I only have one hardware thread, then I can only execute one instruction at any given time. If I had two hardware threads, then I could run executions or execute instructions in parallel. You get it? Now my machine is an 8 hardware thread machine. So technically I can run 8 instructions in parallel at any given time. But for now, let's imagine that our hardware is single hardware threaded. Now that's at the hardware level. We've got to, in our operating system scheduler, leverage this. So what we're going to do is we're going to define the idea of an operating system thread. If there's going to be a hardware thread, we're going to represent the idea of an operating system thread, our own thread. And I always want us to think of threads as paths of execution. So our program is going to be a series of instructions. Those instructions are laid out to execute in sequence, and it's the job of the thread, our operating system thread right now, to execute those instructions one at a time, do the accounting, and to leverage this hardware thread to do it. So the operating system is going to execute those instructions in sequence, leveraging the hardware thread that does the actual execution. All right? Now, when we think about these operating system threads, we're going to have 3 different states that operating system thread can be in. And there's a lot more, really, like substates. But remember, we don't have to have full understandings of implementation details here. What we need are good mental models of how things work and behave, and that will help us make better engineering decisions. So there's going to be 3 states that a thread can be in. A thread could be in a running state. And when a thread is in a running state, that means we've placed it on this hardware thread right here, and it's executing its instructions that it's responsible for. A thread can be in a runnable state. And when it's in a runnable state, it means that it wants time on that hardware thread. It just has to wait its turn. And then a thread can be in a waiting state. When a thread's in a waiting state, we really consider it kind of off the radar, right? It's gone and it's waiting for something to happen. It could be waiting for the operating system to come back with a system call. It could be waiting for something on the network to come back in, and it's in a waiting state. And from our scheduler's point of view, we only care about threads that are running or runnable, right? Threads that are waiting, don't put any load on us. They're not our concern. Okay. So imagine the following scenario. We have a couple of programs running, which means we have a few threads that are in play. And the idea is that we want to create this illusion, even with one hardware thread, that all the threads that we have that are either in a running or a runnable state are actually running at the same time. So how could we create this illusion with our scheduler? So one idea is that we can define what we'll call a scheduler period. So let's define our scheduler period. Now, the scheduler period, what it's responsible for is our ability to execute any thread that's in a runnable state at the beginning of this period, to get that thread to execute within this time. And if we can do that, then we can create the illusion, at least within the scope of the scheduler period, that everything's running at the same time. Now we could play with some fun numbers here. I'll give you some real numbers for certain things. Other numbers, we'd have to really look at our operating system scheduler to see what they are. But we can use some base numbers to get an idea. And let's just say right now that our scheduler period is going to be, let's just say, 100 milliseconds. Let's just say that that's what we're going to use. Our scheduler period is going to be 100 milliseconds. So the idea is that what we want is to make sure that every thread that we have in a runnable state executes within this 100 millisecond time frame to create the illusion that everything is running at the same time. So let's start off our scheduler. And we do that, and right at the beginning of the scheduler period, what we notice is that we have just one thread in a runnable state. That's all we have. So if we only have one thread in a runnable state, and our hardware only has that single hardware thread, remember, only one thread can physically execute at any given time, then this thread, we'll call this thread A. Thread A is going to get the full 100 milliseconds of time to execute its instructions. It gets the full 100 milliseconds. It's brilliant, right? A whole lot of time to do work. And remember some of the numbers that we talked about earlier in the video. We said that every nanosecond of time, remember that, right? Every nanosecond of time, 1 nanosecond of time equals 12 instructions. I want you to remember that number. 1 nanosecond represents those 12 instructions. Okay, great. So we're going to keep that number in our head as we continue to go through this exercise. Now, we've got the A go routine. It was in a runnable state before that scheduler period started, and now it's off doing its work. Now the scheduler period is done. And once the scheduler period is done, we go back and we look at how many threads we have in a runnable state. Let's say right now we have 2 threads in a runnable state. So what does that mean? Well, it means now that we're going to schedule both threads to execute within our same 100 millisecond scheduler period. So we decide to run thread A again. But we know that thread A is only going to get what? 50 milliseconds this time, which now means that we're going to schedule that other thread, thread B, to run, and thread B is only going to get 50 milliseconds. So let's look at what just happened here. We did create the illusion that 2 threads ran within the scope of our scheduler period. But if we start looking at what's happening to our A thread, it got 100 milliseconds of runtime the first time, but now it got cut in half. Its throughput across the next 100 milliseconds got cut in half. We're not executing as many instructions as we otherwise did in the previous run. Okay, no problem. Let's keep going. Scheduler period is over. We look again, and what do we notice? We notice now that we have five threads now ready to run in a runnable state. So what does that mean? Now means that we've got to cut this down again, right? And so this time, what is thread A going to get? Thread A is only going to get what? It's only going to get 20 milliseconds this time. So now thread A is going to get 20 milliseconds. We now know that thread B that we had is going to get its 20 milliseconds for thread B. And then what are we going to do with that remaining 60 milliseconds here, right? The remaining 60 milliseconds now is going to go across those other threads, C, D, and E, right? That's going to be the remainder of that 60 milliseconds of time. And I want you to notice again that every time more threads show up to be run within this scheduler period, the time starts to get smaller and smaller and smaller, right? If eventually we had 100 threads that wanted to run within this scheduler period, we had 100 threads. We're now at the point where this thread right here, thread A, is going to be down to what? 1 millisecond of time, 1 millisecond of runtime. And what that means is that at some point, there's going to be a diminishing return on the time a given thread really gets to do any work. And it's mainly because there's a cost here that I haven't touched upon, and that is the context switch cost. Now, think about this for a second. We have thread A, and thread A is coming in and says, okay, I want time on this hardware thread. So we go in here and we place A on the hardware thread, and it's doing its work for that 100 milliseconds. And now we decide, okay, now thread B is going to run for its, let's say, 1 millisecond. Well, we've got to take some time to pull this thread off the hardware, right? And then we've got to put this thread on the hardware. I mean, that's not free. That's going to take some time. This is what we call a context switch, taking one thread off, putting another thread on. Now, on average at the operating system level, a context switch like this is going to be anywhere from 1 millisecond to 2 milliseconds. In other words, 1,000 nanoseconds to 2,000 nanoseconds. Let's start doing the math again. Remember, a nanosecond of time represents 12 instructions. So what are we looking at here when we talk about a 1 to 2 millisecond context switch? What we're talking about here really is a 12,000 to 24,000 instruction loss, right? Instructions we otherwise could have been executing, but we can't because of this context switch. So think about where we're at. If you have this many threads context switching at 1 millisecond, or even worse, what if this gets down to 1,000 threads? Oh my goodness, 1,000 threads. Now we're talking about microseconds, right? Microseconds of time that a thread gets to execute on top of the 1 to 2 microseconds of context switch. What eventually happens is that you're doing more context switch work than you are actual work. And this is not good. So there's a point of diminishing return where that time slice gets to a point where, and the number of threads, where you're doing more context switch work than actual work, and we're not really getting any throughput from the machine or our apps. So what are we going to do? Because if we just stick with a scheduler period of 100 milliseconds and we end up getting 500 to 1,000 threads that we have to schedule, we just said none of this is going to work. That's a huge loss. So what we're going to have to do in our scheduler is define another parameter. And what we'll do is we'll define the minimal time slice. In other words, this is the bare minimum time slice, regardless of our scheduler period time, that will allow any thread to at least get some runtime. And maybe what we'll say is 10 milliseconds is that point of diminishing return. We never really want to go below 10 milliseconds of a time slice, because once we get below the 10 millisecond time slice, our context switches are actually really causing our performance problem like we discussed. But that gets interesting now, because if we think about a minimum of a 10 millisecond time slice, remember we were at 100 threads right here. We were at 100 threads. So now we're never going to dip below that 10 millisecond. So what does that mean for 100 threads? It means that our scheduler period is no longer going to be 10 milliseconds over 100 threads, right? It's going to be what, like 10 seconds? So start thinking about that for a second. Even though we had this scheduler period that gave us this reasonable amount of time to create the illusion, once we get to those 100 threads with a minimal time slice of 10 milliseconds, right? Now we start realizing that our scheduler period is in the seconds, like 10 seconds to create this illusion. That's not necessarily working for us either, right? Now we also going to start feeling some throughput issues, because any given thread might have to wait a total of 10 seconds before it even what? gets to run again. All right, you can see how complicated this stuff is. So in this world, it's always going to be about less is more. Less is more. The less threads that we have to schedule and during any given scheduler period means that each thread's going to get more time, and that thread's going to be able to come back into play sooner. So we're always needing to balance out this idea, all right, this idea on the operating system side. Now, there's another concept that we really do have to understand if you're going to be a multi-threaded software developer, and that's workload. And there are two types of workloads that we've got to be able to identify early on if we're going to be making smart engineering decisions here with our scheduler. The first type of workload is called CPU bound. Now, a CPU bound workload is a workload where a thread naturally does not move into a waiting state. It never moves into a waiting state. So an example of a CPU-bound workload would be an algorithm that's going to be counting integers. So imagine I gave you a list of 1 million integers, and I said, hey, count these integers up from beginning to end. There is nothing in the processing of adding that would cause the thread to naturally pause or wait for anything. That's a CPU-bound workload. And what that means is that every thread is going to get its full time slice all the time. Essentially, what I've been describing here is a CPU-bound workload, where when the A thread gets on the hardware thread, it's going to get its full time slice from beginning to end, and it won't be switched off until that time slice is over. Now, the opposite of a CPU-bound workload is what we would call an I/O-bound or blocking workload. And these I/O-bound workloads are workloads where the thread never actually uses its full time slice, because at some point within the scope of its time slice, it's going to make a call to the operating system over the network. It's going to do something that will cause it to move from a running state into a waiting state. Now, in those situations, even if I had 100 threads, right, or I had 1,000 threads, the chances of the scheduler period over 1,000 threads in our simulated operating system here getting to 10 seconds is pretty slim, because most likely that thread very early on, maybe within its first millisecond or so, will make that call to the operating system maybe to read something over the network, and immediately it will get context switched out. When it comes to these I/O-bound workloads, the context switches actually are our friend. Right? When it comes to CPU-bound workloads, the context switches are hurting us. Think about that. It's hurting us because we're going to be taking these 12,000 to 24,000 instruction hits for every context switch. And those instructions could have been work that we otherwise could have been doing. But when it comes to an I/O-bound workload, the context switches are our friend. Because since the thread is going to be stalling out, right, it's going to go into a waiting state, which would keep the hardware thread idle, we can now leverage those 12,000 to 24,000 instructions to do the context switch to get another thread up and running. So that's why understanding our workload is so important. Because if it's a CPU-bound workload, then we really don't ever want more threads than we have hardware threads, because the context switch is hurting us. It's extending that scheduler period out, and it's causing that throughput issue the more threads you have. But if it's an I/O-bound workload, now these context switches are our friend. They're helping us get more work done faster because we're not allowing the CPU, or in this case the hardware thread, to stay idle. Now, just as a small side note, you have to understand that our operating system scheduler is going to be a preemptive scheduler. Now, what does that mean? What it means is that the operating system has to handle events. Think about it. Your hardware is dealing with events all the time. I mean, just the clock. Just to keep the clock up to date, there is an event that's occurring on the machine. And every time an event occurs on the machine, a thread has to respond to it. So part of our scheduler also is going to have to create a mapping of hardware events to operating system threads and setting certain operating system threads to have a high priority. So even if we were doing a CPU-bound workload here, even if we're doing this CPU-bound workload, every time the clock has to run, we will have to interrupt that workload, get the thread for the clock to run quickly, do its thing, and pull it off. Now, I don't want the fact that we have a preemptive scheduler that's event-based to get in the way of our mental models. And we're not going to. We're going to forget about that. But it does lend something that we do have to understand, and that is scheduling is unpredictable. When all things are equal, we never really know what the scheduler is going to do. And we're going to have to keep that in our heads while we design code, because no matter what we're doing, especially in multi-threaded software, there has to be moments of guarantees. And it's going to be our job to deal with synchronization and orchestration. In other words, putting points of guarantees in the code so we can guarantee that the algorithms do run, even if they're executing out of order, they do run correctly. So even though it's a preemptive scheduler, I want to kind of throw that out. Let's just forget about that right now, and we'll just focus on those ideas of CPU bound and IO bound and what they mean. All right, so we now understand a little bit about our scheduling period, wanting to create the illusion that all threads are running at the same time. We now understand that there is a point of diminishing return when the time slice gets too small, and that's because our context switch, which is causing us 12,000 to 24,000 instruction losses, eventually catch up with us. So as a scheduler, we're going to have to tune these numbers. But for our purpose right now, the 1 to 2 microsecond latency cost on a context switch is a really good number for us to use. We'd have to really look at what our time slice and scheduler periods are for the operating system. But regardless of what they are, this model is a good mental model to work with. So let's sum up a little bit here by thinking about two algorithms that will help us better understand this. So there's two algorithms that we can play with, a CPU-bound one and an IO-bound one. So let's focus on our CPU-bound algorithm first. So let's say that I truly did ask you to write an algorithm that can take a collection of numbers, let's say 1,000,000 numbers. Here it is. Let's draw that collection up. There it is. A big collection of 1,000,000 numbers, integers. And I say to you, I want you to add up every number in this collection and then tell me what the value is. Now, anytime we're going to be doing anything like this, especially around multi-threaded software, the first thing we need to do is write a sequential version of the algorithm. So writing a sequential version of add, basically, would be about 5 lines of code, right? We're going to range over this collection. It's integer-based. We'll use our value semantics around our iteration. We'll have a local variable, and we'll add into it. So the sequential version just says, start from the beginning, go to the end, 5 lines of code, and we're done. And now that we have a sequential version, the next question is always going to be, is this work that can be done concurrently? Now, let's talk about that again. Concurrency means out-of-order execution. So now we can come back and say, does it matter what order I add these integers in? Will that affect the final result? Now, when it comes to adding a collection of integers, the answer is no. We can do concurrent work here. It doesn't matter what order I add these integers up in, as long as we add them all up. That's really cool. We do have a problem in front of us that can leverage concurrency, right? One idea could be no problem. I could split the list in half, right? And I can say, let's get one of our operating system threads to add this half. I can get another operating system thread to add that half out of order. And then we can take that and sum those two values and get that result. In fact, I could argue that I could break this up in multiple lists and multiple threads. And you may be like, wow, yeah, we can get a bunch of threads. Maybe we can get 100 threads adding small sections of numbers up and then do the add. That would be brilliant. It could be. But remember, the only reason to add this level of complexity, and trust me, there's complexity here, is because we can get the work done faster. We can get some better throughput. Now, let's go back to the idea of parallelism. Remember, parallelism means executing instructions at the same time, 2 or more, right? It's being able to do work at the same time, right? That's what we're talking about here. So let's go back to our imaginary hardware for a second. Remember, our imaginary hardware is just a single hardware thread. That's it. which means how many threads can I execute at any given time physically? And the answer is 1. Only one thread can execute at any given time. So think about this for a second. I have this array of 1,000,000 integers. Let's say I do break it up into 4 lists here, and I throw a thread at every list. Thread, 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 thread. Question: will running this algorithm sequentially be faster or slower than running it in parallel with 4 threads when we have a single hardware? Think about that. Because this is CPU bound, and because I can physically only execute 1 thread at a time, running the sequential version is going to be faster. Because every time we have to swap that thread off, and it's going to have to do that 4 times, right? Every time we swap that thread off the hardware, what are we taking? We're taking that 12,000 instruction loss. There it is, 12,000 instruction losses. And that's to say that that got all that work done within the time slice. If it didn't, we're going to incur more of these 12,000 instruction losses. And think about it. These are 12,000 instructions that we could have been using to add integers that we are now not. So one thing you need to understand here with CPU-bound workloads, if we only have 1 hardware thread, then we really can only run 1 operating system thread efficiently. But what if I change my hardware? What if I turn my hardware into a 2 hardware thread processor? Here it is. Now how many threads can I run? I can run 2 threads in parallel. Think about this now. Think about it now. Now, the fact that this is concurrent gets interesting to me, because since I can run 2 threads in parallel, I could now break this list up in half, give this thread and this thread its own list, right? They can run in parallel. We could get this work done now at the same time. Then we come up and we get our value. Now, if I had 4 hardware threads, now I could use 4 operating system threads and get it done even faster. So one of the things I want you to recognize here is that when it's a CPU-bound workload, if you want to get more throughput, then, and the algorithm is concurrent, then you need parallelism, right? This is where I said that sometimes these words blend and sometimes they don't. Without parallelism, there is no efficiency with concurrency or out-of-order execution because the context switches are hurting us. Yeah. But let's go back to our single hardware thread again. This is it. That's what our hardware looks like. And in this case, let's say that this isn't a list of integers. No. This is a list of URLs, a list of URLs that we want to go fetch and process. What does that mean? This is no longer CPU bound. It is now IO bound work, which means that when any given thread makes that network call, it's going to move into a waiting state. So think about it. If I build that algorithm sequentially, right, it will have some particular amount of time it takes. But since it's IO bound, right, what does that mean? It means that I could break this list up on multiple threads, even if I have 1 hardware thread, and get it done faster. Why? Because now the context switches are helping me, right? This thread starts, maybe it gets 1 millisecond in, and then it makes the network call and it goes into a waiting state. Now what happens? We take our 12,000 instruction hit to pull that thread off and to put this thread on. Up until then, the hardware would have been idle. So now we're 1 millisecond in, but guess what? This gets to start running 1 millisecond in, and now all of these threads are being able to get work done while that processor was going to be idle because all of these threads said, I don't need time anymore. But here's the interesting part about IO-bound workloads. It's really complicated to figure out what is the most efficient number of threads. In other words, there's still a point of diminishing return if you use 2 less, or diminishing return on 2 more. Even if you use 2 less, you're going to have a problem. You have to find what's called that magic number. And really the idea is that, is there a magic number where there's only ever 1 thread really in that runnable state? That's what we're looking for, right? If we only have 1 thread ever in a runnable state, stage to go, then we're going to have the most efficient efficient number of threads for that IO-bound workload. This stuff is very, very complicated. CPU-bound workloads are nice and they're simple and they're really efficient, right? We know that for any CPU-bound workload, the number of threads we use equals the number of hardware threads we use. Their parallelism is important. But when it comes to IO-bound workloads, we don't need parallelism to see improvement with concurrency, because the threads can take turns on this hardware right here, and those context switches are helping us get more work done over time. Again, we don't really know how many. And so when it comes to operating system level stuff like this, we always tended to use thread pools. We use thread pools to do this. I mean, imagine you were building a web service and you decided to create an operating system thread for every request that came into the server. And you had 50,000 requests coming in. I mean, we were playing with just 100 threads. Imagine 50,000 threads, what that problem would cause. It wouldn't work, right? So we would want to have a pool of threads that we would post work into, and we've got to find that magic number. We've got to find the number where if we use too many threads, now the context switches are hurting us. We have too many threads in a runnable state, right? If we use too low of a number, then we're also going to not perform very well, because now we're going to have more idle time on the processor because I don't have a thread that's ready to go. These are complicated problems at the operating system level. Okay, so just to recap a little bit here. Concurrency means out-of-order execution. All right? And parallelism means executing two or more instructions at the same time. We have to know what state a thread is in, and we have to know if our workload is IO-bound or CPU-bound. CPU-bound workloads mean that threads don't naturally move into waiting states, which means that we need parallelism to get any throughput with concurrency. IO-bound workloads mean that threads do naturally move into waiting states. That means that we do not need parallelism, right, for that concurrency to give us throughput, that the context switch is helping us get more work done even on our single-threaded hardware. These are things that we're going to want to carry on. And just finalizing, remember that CPU-bound workloads are the most efficient workloads that we could do on the machine. So the next thing for us to now do is talk about the Go scheduler and how that sits on top of the operating system and some of those mechanical sympathies that we're going to need as Go developers to make sure that our algorithms and work are going to be efficient with the Go scheduler that's sitting on top of the operating system scheduler that's sitting on top of the hardware.